The common image of machine learning is a glowing, synthetic brain slowly waking up. In practice, this process is purely mechanical. Supervised learning operates as a finite-dimensional, unconstrained mathematical optimization problem. The engine of every model is the empirical risk function. This equation measures the distance between a model's predictions and the true data labels across n individual samples. This mathematical goal describes a spatial search. The algorithm moves through a vast landscape, looking for a specific parameter configuration known as theta star. This optimal configuration represents the coordinate in space where the empirical error reaches its minimum value. Neural networks function by executing a massive, blind mathematical search governed entirely by local gradients. We can visualize this parameter space as a geographic landscape. Peaks represent configurations with a high error rate, while valleys represent low error. When we initialize a model, we drop a blindfolded agent onto a random point on this map. This agent has no access to the global layout. It can only sense the immediate slope of the terrain directly beneath its feet. The ultimate destination is the global minimum, the absolute lowest valley in the landscape. This creates a mechanical challenge, finding the absolute bottom of a space with over 100 million dimensions using only local, tactile information. The negative gradient serves as the primary oracle, pointing the agent towards the steepest descent. This movement is dictated by the gradient descent update rule, which maps the agent's next position. The agent senses the slope and takes a step in the direction of that vector. However, the gradient oracle only provides direction. It provides no information about how far the agent should travel. The human architect must provide this distance information through the learning rate, a blind assumption of step length. A learning rate that is too small leads to tiny steps. The agent stalls on the slope, making almost no progress. This conservative step size requires so many iterations that training becomes computationally unfeasible. Conversely, an overly large learning rate leads to massive steps. The agent overshoots the valley and begins violently oscillating, climbing higher with every jump. This aggressive step size eventually causes the algorithm to diverge entirely, missing the minimum and breaking the model. Even in a perfect convex environment, gradient descent is fragile. Success depends entirely on the accuracy of the human-chosen step size. Real-world datasets complicate this. Imagine millions of data points as millions of independent voices, all shouting directional vectors at once. Calculating the exact mean gradient across all these samples for every microstep is mathematically intractable at scale. To solve this, researchers use stochastic gradient descent. Stochastic gradient descent functions by randomly sampling just one or a small batch of data points per step. Each random sample is a point-noisy approximation of the true gradient, which forces the descent path to become jagged and erratic. Injecting this mathematical noise drastically reduces memory and compute costs, allowing the agent to move through the space with much higher frequency. Modern machine learning trades precise direction for noisy, continuous momentum. The smooth, convex bowl is just a theoretical simplification. In reality, real neural network loss landscapes are infinitely more complex. This complexity creates shallow local minima where the gradient evaluates to zero. Standard stochastic algorithms get permanently stuck in these suboptimal points, mistakenly treating them as the absolute bottom. Polyak's heavy ball method solves this by mapping physical mass onto the algorithm. The beta term adds inertia, allowing the agent to remember its previous velocity, as if the terrain were frictionless. When the agent enters a shallow local valley, its accumulated kinetic energy carries it up and out the other side. It clears the ridge of the trap and falls into the deeper global minimum. Momentum provides the mechanism to differentiate between a temporary dip and the true objective, enabling the model to escape mathematical dead ends. The final challenge is overfitting, a configuration that memorizes training data but fails completely on unseen data. A model that perfectly hits every single training data point is often brittle. It has captured noise rather than the underlying trend. In high-dimensional space, the absolute deepest minimum is often a narrow, overfitted crevice. To counter this, architects often keep the learning rate constant instead of decaying it to zero as the search concludes. This forced stride causes the agent to circle the minimum continuously, stepping over the exact center without ever settling into it. This specific avoidance behavior provides what is known as implicit regularization. This continuous oscillation encourages the agent to discover wider, flatter, and mathematically robust regions of the landscape. Intentionally avoiding absolute perfection on the training data provides the necessary overhead for a model to generalize to the real world. Pulling back reveals the entire optimization system working in unison. Local gradients provide directional light in a massive, blind search. Stochastic sampling allows that search to occur at scale by trading precision for speed. Momentum prevents the process from stalling in false valleys, and constant motion ensures the model finds generalized, robust answers rather than brittle ones. State-of-the-art artificial intelligence emerges from the integration of applied calculus, stochastic probability, and massive, iterative mechanical search.